Hello again, welcome to another lesson in Algebra 1. Today we are covering the guided notes on Module 1, Lesson 6. And if you've been following along for our course, notice we skipped two lessons for Module 1. We skipped Lesson 4, which is just a review of a nonlinear problem. So kind of a culminating problem, and we actually are going to do that in class, you'll see when. And then Lesson 5 was an introduction to systems of equations again that you did from Math 8. We're going to hold off on that lesson until we get to our systems of equations unit this year. All right, so we're starting in on Lesson 6, and you had a warm-up here for Lesson 6. In class, we were to create equivalent expressions for each of the positive integers below. So for instance, we could do 2 and just plain 2, or 3 could have been 1 plus 2, and so forth. Okay. Now we were only allowed to use those numbers 1, 2, 3, 4 at most once. So at most once means we didn't have to use them at all, but we could only use them one time. And we were allowed the operators of addition and multiplication as well as grouping symbols in parentheses. So the first three are done for you already. If you haven't done this yet and you're at home watching the notes or learning the notes for the first time, you should really pause the video and try these. It's good practice of your number skills. And then come back and you can check some answers. There are multiple ways to do them, but just be careful that your order of operations are happening. So in other words, all your grouping symbols happen first, and then multiplication second, and then addition third. Okay? Since we don't have any subtraction or division, then just forget those. Okay? All right, so once you've checked them over, let's go down to number 1 here. So 1 plus 2 plus 3 equals 6. And so does 1 times 2 times 3. Does that equal also 6? Is it true that for any numbers a, b, and c that the sum of their products are equal? Notice that for the first part of this problem, a is 1, b is 2, c is 3. So in other words, this said a plus b plus c, and then we could see which ones they were. And this one said a times b times c. So we want to know if that always works. So is a plus b plus c always going to be equal to a times b times c? Well, this is easy to prove false because all we have to do is come up with some other example that doesn't work. And we can leave a and b be the same. So we could say a is 1, b stays 2, but let's make c be 4 this time. And we'll prove that this does not work. Okay, so if we plug in our new values for a, b, c that we picked, we could show that this statement is not always going to be true. So I'm going to put in 1 for a, and 2 for b, and 4 for c. And we're going to test, is this equal to 1 times 2 times 4? Okay, so this is a test here, so we're going to put a question mark over the equals. And my smartboard's off a little bit, but that should be right over the equals. 1 plus 2 plus 4 is going to make 7. And that is definitely not going to equal to 1 times 2 times 4, which is 8. Okay, so is the sum always going to be the same? And it's going to be no. The sum will rarely be the same as the product. Okay, it just only worked for 1, 2, 3. Okay, all right, so how can we show geometrically that these are not equivalent? So geometrically, when you do 1 plus 2 plus 3, what we're doing is, or a plus b plus c, is we're lining up 3 segments, okay, into one long segment and then measuring the length of the long one. So our total length here is a plus b plus c. But when we're doing a times b times c, what we're doing is really finding out the volume, or how many little cubes will fit inside of this rectangular prism that we are creating here. So the volume is, remember, is the area of the bottom, which is a times b because it's a rectangle, times the height of that rectangular prism. And these are not going to be the same. So obviously finding the length of 3 segments is not the same as finding the volume of a rectangular prism where the sides of the rectangular prism are the same lengths of the segments. All right, let's flip it over and take a look at the second page. Okay, at the top of the second page, we have the distributive property definition. So the distributive property states that for any numbers a, b, and c, then a parentheses b plus c is the same as a times b plus a times c. Because addition can be written as subtraction, so inside we could just change that to minus negative c, so subtract the opposite, then we can also be a times parentheses b minus c is the same as ab minus ac. So it's just the same rule but written in a little bit different when I do subtraction. So you've learned this a couple times over your math career. So remember when you multiply something times the sum of some other stuff, all we have to do is multiply to each entry inside of the sum part. So we just think of it as hopping the fence to go multiply to the other guys. So you use the distributive property to write equivalent statements for each to demonstrate how like terms are collected with addition and subtraction. The first one is done for you. So for instance, if we're adding 2x plus 3x, we learned last year that we just add the numbers in front, 2 plus 3, and then put the x back, and we would say 5x. The reason this works is because of the distributive property. What we're really doing is distributing out the x. So we're taking the x backwards. We had an x in both of them, just like this a. So we pull the x out on the outside. We left behind 2 plus 3. And then we can add 2 plus 3 to make 5. So we get 5x. Okay. So for part B, if I want to combine 5t plus 8t, I can use the distributive property to show how that works by undistributing the t. Okay. That will leave behind 5 plus 8. I'm going to write the t in the back, although we could have put it in the front there. And then 5 plus 8 is the same as 13. So we get 13t. Okay. Now remember, we can only do this if we have the same variables for both parts. So 2x, just x with an exponent of 1, and 3x, x with an exponent of 1. If they have different exponents or different variables, it doesn't work because I can't undistribute different things at the same time. So here we have c squared the same in both. So I can take out the c squared. That would leave behind 7 minus 4. And then c squared's now been taken out, undistribute it. And then 7 minus 4 is 3, so that becomes 3c squared. Same thing with our last one. We can undistribute the x. Notice it's really distributive property, but I like to call it undistributing because we're taking it out instead of putting it back in. So this is going to become 9 minus 2 times x, which is 7x. So use the distributive property to remove parentheses in a mathematical expression. So sometimes we want to get rid of the parentheses even though the inside can't be added together. So up here we added our own parentheses, but we could get rid of them by adding the insides together. Now we can't. So the way to get rid of it is go ahead and use the distributive property. So we'll distribute the 3 to here. 3 times 2 is 6, and remember we did not change the variable. And then 3 times 5 is 15. So we can distribute that 3, and now our parentheses are gone. 6x plus 15 is our final answer. Okay, so we can distribute, we could show this geometrically, okay, how that works. So we're doing 3 times 2x plus 5. So we rewrite 2x plus 5 as x plus x plus 5. So this is the length of x plus 5. So an x, another x, and a 5. Okay, and then we're timesing that by 3, so we'll build a little multiplication box to help us fill it in. That's what we did here. So we do 3 times x, that's here, 3x, same as here. 3 times x again would give us 3x, and 3 times 5 would give us 15, same as up here. All right, so you can build your own boxes for these. You don't have to have me build it for you on the notes. And then when we're done, you can see these two can be combined because they're like terms. So they become 6x, and then we still have 15 left over. Okay. Now, real quick, we didn't have to write the x's separately. We could have done this. We could have said this box is 2x long, and this box is 5. And then we say 3 times 2x is 6x, and 3 times 5 is 15. I showed this one for you guys who read the module. This is the way they first show it to you. Okay. All right, use the distributive property to remove the parentheses in each of the mathematical statements here. So we're going to go ahead and do our distributive property. So this is 2 times x for 2x and 2 times 4 for 8. If we were to show it geometrically, it would look like this. 2 on the outside, x and 4 up here. 2 times x for 2x, 2 times 4 for 8, and then we copy out those middle ones. 2x plus 8 for our final answer. Okay, so for part B, I'm going to show it geometrically first. And then we'll go back and show it with the distributive property hopping over the fence. So negative 3 times 2m will give us negative 6m. And negative 3 times negative 5 will give us positive 15. We know the inside is our answer, so this is going to say negative 6m plus 15. Okay, you could get that same answer by taking the negative 3 and timesing it to that term and to that term. Okay, and remember, negative times a negative will give us a positive. All right, part C. Let's just do it the shortcut way, so hop the fence. 20 times 0.5, so half of 20 is 10. And then 20 times negative 3 will give us negative 60. And then here we have a fraction, but we can do this on our calculators. So negative 3/2 times 2 would give us negative 3. Keep the y there with it. And negative 3/2 times 8 will give us negative 12. So that should say negative 12 there, so minus 12. All right, so here we have a question by Leela. And Leela is convinced that y times y plus 3 should equal to 2y plus 3y, which is the same as 5y. And we wanted to demonstrate geometrically why she is incorrect. Okay. So she thinks that if I multiply this y times this y, I should get 2y. It's two of those y's there, right? And then y times 3 will give us 3y, and then you can add them up and get 5y. That's what she's seeing. All right, so we have to be careful. Geometrically, it's easier to see this. Y times y is not 2y's. This is y squared. So think of it as a square, same area, so same sides on each one. So if this was a square like this, 5 by 5, the area would be 25, not 2 times 5. Or if it was a square that was 6 by 6, its area would be 36, not 2 times 6. So this is where she made her mistake, is saying that y times y was 2y. It's really y squared. And then y times 3 is 3y. So our final answer here should have been for Leela, y squared plus 3y. All right, this concludes our second page of notes. Let's flip it over and see what we have to do on the third one. Okay, so on our third page, Leela is convinced that a plus b in parentheses squared is the same as a squared plus b squared. We just move the squareds over and call it good. Okay, so this is one of the most common errors in Algebra 1. Okay, so this actually doesn't make a squared plus b squared, and we're going to try to draw a picture to illustrate why her reasoning is incorrect. Okay, so let's just start with something squared. So we know 5 squared, we would do a picture for this, and that would be 5 plus times 5 here for 25, right? So we're saying a plus b times a plus b, because that would be the same thing, right? A plus b is our 5. So let's make our square. This is a plus b. Well, a plus b is a length, 2 lengths added together, so we have to break this up. So that's length a and that's length b. And then we have to do the same thing here, a plus b, so we have to break it up this way. So length a and then length b. Okay, now a and b could be the same length or they could be different lengths, so we could draw our square like this. Let's see if I can get rid of that stuff. Okay, so this could be a's length and this could be b's length. And then we do the same thing. This is still a and here's still b, and when I'm done, I get this square. Now for us it doesn't matter, we're just trying to show how it works. So what is a times a? Well, a times a is a squared, and a times b is just that, a dot b, okay, or we don't have to need the dot there at all. And then b times a would be the same thing, but we just put the a first, so we'll call it ab again. And b times b is b squared, okay? So now when I put all my little pieces of the box together, we're going to get a squared plus 2ab plus b squared. All right, so let's show how that works with these 5s here. So if we could break 5 into 2 numbers. We could break 5 into 1 and 4, right? So this would be 1 and 4. 1 plus 4 on the side, 1 plus 4 on the top, and that's still 5 times 5. So this becomes 1, 4, 4, and 16. Okay, and then we combine them all together. That's 1 plus 2 times 4, because there's 2 4s there, plus 16. And together that still makes 25. That's why we have two ABs here, because they're the same, okay? Okay, so keeping with the same pattern above, we're going to do number 9 here, where we're going to draw a picture to help us show how this works. So we're multiplying A plus B plus 1 times B plus 1. All right, so we'll make our box to help us. So this is actually called the tabular method to help with distributing. Okay, and we're going to fill this in. So we have A times B in our first box, or B times A. Always try to write them alphabetical, then we will put them together, it's easier. In our top middle box, we do B times B, but anything times itself is just that number squared. And then the top right is B times 1, which is just a plain B. Okay. And then down below, we have 1 times A, which is just plain A, 1 times B, which is just a plain B, and 1 times 1, which is just a plain 1. Okay, so we got to put all these together. We're going to start with the biggest terms, so B squared and AB should go first. Okay, so those are both have exponents of 2 combined as a term. So remember, that's a 1 exponent and a 1 exponent, even though we don't write them. So together they make a degree 2. And then we put the B squared with it. Okay, and then we can put the A. And then we have 2 B's, so we have to put 2B, and then we have a 1. Okay, so we can combine the 2 like terms in these spots to make 2B. All right. Now, last one on this page, number 10, draw a picture to represent A plus B times C plus D times E plus F plus G. So this is a very hard picture to draw. Okay, so this one is actually going to be finding the volume. So I'm going to draw the picture the best I can, and then we'll see what's going on with it. All right, so we have A plus B. That's this way. Okay, and then we have a C plus D, and we're going to draw this 3D. So this is a C plus D going this way. This is why this picture is kind of hard to draw. And then we have an EFG tall. All right, so this is E plus F plus G tall. So we have this picture going on. And we're going to find this rectangular prism and try to find its volume. All right. That's not too bad. Let's see, I still need a line going down this way. So there are, and I should probably put the GFE out here to make it easier to see. GFE, 9, oh wait, nope. There are 6 in the front boxes and then 6 behind boxes. And we have to find the volume of each one of those little cubes to figure out what our total volume is. Okay. All right, let's give it a try. So up in the front here, this box is going to be A times C. Okay. So, and then we'd have B times C. And then right above it, we have, oh, nope, that's A times C times G, B times C times G. And then right above it, we have A, C deep, and then F tall. So A, C, F. And then we have B, C deep, and F tall. So B, C, F, and that is hard to read with my smartboard acting up here. And then on the very top, we have A, C, E for this area, or this volume, and B, C, E for this volume. Okay, so that gives us 6 pieces. Now there's also 6 more, okay, for the back part here. And some of them are hidden from view from us. We can't see them. So one of them here we can see. This is A, B by D by G. So this is B, D, G right here, okay? And this one is B, C, G, but we've already got him. So this back one. So let's go through and see if we can't find them all. So I know I have A, C, G in the front left box. I have a B, C, G in the front bottom right box. I have an A, C, F, and the top or the middle front left box, and a B, C, F in the middle front right box, and then an ACE in the middle top front left box, and a BCE in the top front right box. Okay, and now we got to get the back ones. So bottom left in the very back, that's A by D by G. Okay. Bottom on the right in the very back is B by D by G. Okay. Middle on the back on the very left side, so middle back left is A by D by F. Okay. Middle in the back on the right is B by D by F. And on the top there, we have A, the top on the left in the back is A, okay, by D by E. And on the top back right, we have A by B by D by E. All right. So I find that very hard and confusing to do. None of these are like terms, so they don't add up and go together. Notice when we're done, we should have 12 of them. Let's count them just to make sure we didn't miss one, because there are 12 cubes inside of this big cube. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It looks like we got them all. And we're basically finding the volume of each one of those little rectangular prisms inside the big rectangular prism. So that is hard to do. So you can do these with the distributive property. So for number 11, it says redo exercise 8 to illustrate why Leela was incorrect by using the distributive property to remove the parentheses. So number 8 said a plus b squared. Okay, so let's try that with the distributive property. And sometimes it's easier with the tabular method, and sometimes it's way easier with the distributive property, especially if it ends up being a cubic one like number 10. So a plus b squared is the same as a plus b times a plus b. Now, we have two sets of parentheses. So what I'm going to do is I'm going to distribute this first set to a and then to b. So I'm going to have the a that was inside here times the stuff that got multiplied by it. And then I'm going to have the b that was inside here times the stuff that got multiplied, a plus b. And then I can do the distributive property again on each one of these. So let's do that in green here so you can see it differently. A times a is a squared. A times b is ab. B times a is ab still. Let's do alphabetical order. And b times b is b squared. And you can see we have two ab's that are exactly the same in the middle, so we just combine them. So a squared plus 2ab plus b squared. Now in your homework, you're going to be asked to use both ways, and I tried not to give you the cubic ones, the ones that make the big ones. Okay, we'll have to practice one sometime. Okay, but those are a bit more difficult to do with the picture. Okay. All right, so for the picture ones, I tried not to give you that one. Now, number 12, consider x plus y plus 3 times y plus 1. So we're going to do our tabular method. I think that's the easiest one, and that's what it asks us to do, is draw a picture for this one. So this is x, y, and 3. And by the way, it doesn't matter whether you make that the top of the table or the side of the table. You're still going to get the same answer in the end. And then this is y and plus 1. So we're going to get x times y. We'll put it in alphabetical order. We're going to get y squared, and we're going to get 3y when I times all those together. And here we're going to get 1 times x for x, 1 times y for y, and 1 times 3 for 3. Okay, so if we combine our like terms, which there aren't any, so we just have to write it out. So this is xy plus y squared plus 3, and we should put it alphabetical first, so let's put this x first. X plus, ooh, and I was wrong, there are some like terms here. 3y and y will add up to 4y. And then we have this last 3 coming down, okay? So we end up with xy plus y squared plus x plus 4y plus 3, all right? Now, we're going to do this same problem, but with the distributive property. So let's write it over again. X plus y plus 3 times y plus 1, okay? And I'm going to distribute this thing to both the y and the 1. So we're going to get y times x plus y plus 3. And we're going to get 1 times x plus y plus 3. Okay? So multiplying the y in will give us xy. Y times y gives us y squared, so we're distributing again. So y times x, y times 1, y times 3, which gives us xy, y squared, and 3y. And then we do the same thing here. 1 times x for 1x, 1 times y for 1y, and 1 times 3 for, well, 1, 3, so just 3 there. And then we can combine these two like terms here, 3y and 1y. So this will become xy plus y squared plus 4y. Oh, we should put the x first, alphabetical order. X plus 4y plus 3. Okay. All right. So both answers are the same. And you will have to do this in your homework where you do both the tabular method, or the picture is what they'll call it, and the distributive property method by actually writing out equivalent expressions using the distributive property. All right, don't forget to combine your like terms at the same time. And your homework was exercise 1. And then you skip over 2 and 3, and then you do 4 through 6. And there's a recording paper for you. All right, I'll see you in class next time.